In this lesson, I cover lightweight logging. In general, logging is an important tool for maintainability because it lets you know what's going on inside your system. And as we shall see, lightweight logging can be especially important for software maintainability for problems in the field or problems in general that are difficult to reproduce. To be clear, I already have a traditional logging system that works fine, but it really isn't designed for this purpose. It has a lot of runtime overhead, and that makes it unsuitable for what we want. So a lightweight logging is a parallel logging system that is for a different purpose. So let me quickly go through the outline. I start with an introduction. Then there's a small set of requirements for lightweight logging. Then I describe the usage from the developer's viewpoint. Then a high-level design, the C-level API, the implementation, then I do a demo of lightweight logging, and finally I give some prompts or questions for you to consider, and then I give you my take on them. Lightweight logging is a mechanism to record software activity in a way that uses low amounts of CPU real-time and memory compared to traditional logging utilities. Now, this is just my name for it, and there are probably lots of other names that people use. And there are also lots of implementations of this around, but I'm not aware of a de facto standard implementation. People tend to do their own thing, like I have done a number of times in my career, because it's not super difficult to implement. And in embedded, you're just sort of used to doing your own thing in many cases. So the objective of LWL is that it can be enabled on a product running in the field without affecting its operation. Now, this is not the case with traditional logging, where you often have to be extremely careful with using it on a live system. So taking this objective a step further, we would like to have it enabled always. So it is simply part of product operation. And this is the key. You never know when you want logs, so the ideal case is you always have them enabled. Now, LWL typically writes to a circular buffer and RAM. This is a big part of how we achieve low overhead, and we'll be talking about this later. A major use case of LWL is to see what the system was doing immediately preceding some fault. For example, a watchdog triggered. And for this use case, you can compare lightweight logging to the flight recorder used on aircraft. And this is the use case we'll be focusing on in this course. With LWL, offline formatting tools are typically used to make the log data easy to read. And the formatting tool typically needs access to the source code to get information about the log statements, for example, the format string. We'll see how this works later in this lesson. Here is a list of requirements for lightweight logging. And I want to say, first of all, I will admit these are based on my personal preferences, and you or your team might have different requirements based on the product and your preferences. So let's first take a look at usage from a developer viewpoint. First, we want a printf-like API, as that's what all C programmers are familiar with. And we want to make it reasonably simple to add log statements to a file. Again, the goal is to make it as easy as adding a printf. We don't quite achieve that, but we're fairly close. We also want to make this usable at both base level processing as well as in interrupts. Because in bare metal, we tend to deal a lot with interrupt functions, so that's important. So now let's look at some of the requirements for achieving low overhead. First, there can be no runtime formatting of log messages. This is things like converting integers to text and so forth that are part of an actual printf. And this is a big part of the overhead of logging. So if we don't do runtime formatting, where do we do it? Well, we have an offline formatting tool that will do that, as you'll see later. So you transfer the raw data off of your system, and then you display it, for example, on your laptop. Now, along with the last two requirements, format strings are not to be stored on the system. They shouldn't be in the flash image, for example. That would just be wasted space. We don't need them. We need to support integer-like statements and LWL statements, and integer-like means also enums and booleans and so forth, pointers. The main point is strings and floats are not required. Then finally, the user can specify how many bytes are needed of each parameter. And so, for example, if you're logging an integer, which is 4 bytes, but you know you never have big values in it, maybe bigger than 100, there's no need to store anything other than the least significant byte. And of course, the motivation for this is you're saving space in that circular buffer. So now for some general requirements. The first one is no source file editing during building. And this is a big design choice. The idea is you could have a tool that creates a temporary modified versions of the source files where the logging statements have been converted into code, and then these modified files are the ones that are actually compiled. Now this technique gives a lot of flexibility and can make the API easier to use. And I've worked on a large system that used this technique and it worked well. But I don't really like it because it complicates the build and complicates things overall. In one of the prompts, we will go through some of the advantages that such a system would have. So in this course, we use macros to do these log statements, and you can do things with macros, but it's nothing like what you could do if you edit the source. Then there's a super loop requirement, which basically means it has to be non-blocking because that's the environment we're running in. And then all of the modules I develop, I always want to have support for test and debug. So for instance, console commands to dump the state information and to test the operation. And this note at the bottom just says that storage of the LWL buffer to flash is outside of the LWL module. And we'll see actually in this course, we have something called a fault module, and it's the thing that actually stores the buffer into flash. And of course, the LWL module has to support that by providing a API to get the address of the buffer. I'm going to start with the usage and work down from there. First, it's important to understand that LWL records are identified in the circular buffer using a unique ID. The question from a design point is how you manage those IDs. So here is how I did it. Each file that contains LWL statements must include lines like the two shown below that define the IDs that can be used by this file. If you use more statements than indicated by these two lines, you'll get a compile time error. So in this case, the file has the IDs 20 through 29. So these two lines are needed by the LWL statements below, but the formatting tool also uses them. Currently, the formatting tool requires that literal numbers be used like this, the 20 and the 10. So here is an example of an LWL statement. Of course, this is a sort of a phony example. And we are logging an enumeration in a 16-bit unsigned int. So looking at this LWL statement, it starts with a format string, just like for a printf, although the formatting is actually done in the formatting tool, which is Python, but Python formatting strings are pretty much the same as for C. I'm going to skip this argument for a moment. Now you specify your arguments like you do in printf. This is a variable length list that must agree with the format string. But in this case, for each argument, you must specify the number of bytes to be recorded by using one of these macros, LWL1, LWL2, LWL3, LWL4. So it isn't quite as simple as a printf, but it's not too bad. And having to specify the number of bytes to use for each argument makes for a compact encoding. You want to get as many statements as you can into that circular buffer. So now back to this argument. This is the total number of argument bytes. It is just the sum of these, in this case 1 plus 2. I don't like this because it's redundant information, but I couldn't figure out a way to avoid it, given our requirements. Now, the formatting tool will ensure that this value is consistent with with these arguments. And in general, the formatting tool does check for correctness, and it could be run before the build just to verify there aren't any problems, but it's not required. Here are a few notes about the design. I have a diagram on the next slide to help illustrate this. So LWL information is stored compactly in a circular RAM buffer, as I had mentioned. We want to be able to store as many messages as possible in that buffer. Now, there is a header area uh, with that buffer that indicates the circular buffer size and the current put index into the circular buffer. The put index tells us where to start decoding, as we want to start with the oldest logs. So to view the logs, we dump the LWL data in a raw hexadecimal text format. And this includes the header area that has the put index. Then we take that raw data and we decode it offline using a formatting tool that happens to be written in Python. This formatting tool searches the source code for LWL statements to include the LWL format strings and argument information required to decode the LWL data dump. The formatting tool uses the current put index to find approximately the oldest LWL data, and thus the oldest LWL record. Here we see a diagram of the LWL data and a single record. So this first diagram shows the header and the circular buffer. And in the header, we see the put index, which points to the next byte to be written, and this will be just after the last LWL record written. Now, these LWL records are variable length, and so this put index might point into the middle of an older record that was partially overwritten by this last record written. So when the formatting tool wants to decode this data and it has this put index, it has to be aware that it might not be pointing to the start of a record. And so there's a little bit of a heuristic where it has to find the beginning of a LWL record and sort of get in sync with the LWL records. The other thing to keep in mind when looking at this is that if you have a record, an LWL record that starts here, it may very well be that the record starts here, but then the end of the record is at the top. In other words, it's split across that boundary because of the circular buffer. Now over here is an example of a single record. And what I did here is just use the same example as in the usage slide a few slides ago. And so we're printing or we're invoking the log with a enum, and we want to just record 1 byte, and then this uint16, and we want to record 2 bytes. And so here's what it would look like in memory. The LWL ID would be 20. I'm assuming here this is the first LWL statement in the file. It could be up to 29 in this file. And then the first parameter here, I'm assuming in this case that state_init has a value of 1, and so that takes 1 byte. And then this next parameter is 2 bytes, and we know it's this mask value. And these parameter values happen to be stored in big endian format. So this statement here took a total of 4 bytes of the circular buffer. So here we are in the header file to look at the C API, and I'll just point out a few things. Here is a standard module API used during module startup. And this API here is the function that actually records a log, copies it into the circular buffer. Now the user doesn't normally invoke this directly. They use a macro instead that we'll look at in just a second. This API is called by the fault module. It returns the length and the address of the LWL buffer, and the fault module uses this when it wants to copy that buffer into Flash. So here is the actual macro that the user normally invokes. You can see it then just calls this other macro instead of LWL, it's LWL count. And these macros use a very special feature, underscore underscore counter, and that's not an official C language feature, but the popular C compilers support it. And what it does is every time you access this macro, its value increments by 1. It starts at 0, and as you access it, it increments automatically. So it's a little bit magic. And we use that to generate the LWL IDs. So these two lines here are the key ones for that macro. If logging is active, then it calls LWL rec, which we looked at up here. And then finally, down here are the macros for arguments. And you choose one based on how many bytes you want stored for that argument. And these macros just break the original argument values into separate byte arguments, which are going to be copied into the circular buffer. Here we are in the implementation file, and again, I just want to show you a few things. First, let's look at this data structure, and this is all of the LWL data. There's some length fields in here and the size of the buffer, and then here's a critical field, which is the put index into the buffer, and then this is right here, buff is the circular buffer itself. So the next thing I want to show you is the function that actually records a log. And here it is. There's a critical section here. Here's where the critical section starts. And this is necessary so that while we're recording a log, another function or interrupt or whatever can't come in here and try to do one as well. And there's some words here about how big the critical section has to be. And generally you want critical sections to be as small as possible. In this case, there's sort of a trade-off. I won't go into it, but we make the critical section, at least currently, a little bit bigger than we would absolutely have to for reasons described here. So here's where it's actually writing data into the circular buffer. So it's writing the LWL ID here, and then this loop is writing the argument bytes into the circular buffer. And you'll notice every time we increment the put index, we do a modulo based on the buffer size, and this does the wraparound of the index. And so you can see this is the end of the critical section. And that's it. There's other code in here you can look at if you're interested, including the console commands. So now I want to do a demo, but first I want to show you some of the LWL statements in the code because we'll be seeing this output when we do the demo. So first let's look at the timer module. And here we are in the sysTick handler. This is actually an interrupt handler. It gets called every 1 millisecond. And one of the things we do in this handler is there is an uptime counter, and in milliseconds and seconds. Every time the uptime counter in milliseconds equals 1,000, of course we increment the seconds counter, and we put out a log message of that the uptime seconds has changed, and we include the new value of the uptime counter. And then there's one more thing we do is if the millisecond counter modulo, if it's a multiple of 100, then we just do a log saying tick 100 milliseconds. The purpose of these two logs is just to give you a sense of time when you're looking at the log output. So next I want to look at the LWL module. And here we're looking actually at a console command. This is the LWL test command. This is what happens when you execute that command. It just prints four logs, or it does four logs with different values for the parameters and different lengths of parameters. It uses even values in here, so it's obvious when you look at the output that the arguments are being printed correctly. And after it does those four logs, it freezes logging, turns it off. And then finally, let's look at the temp hum module for the temperature humidity sensor. And the first log I want to show is here. This log will be made when we get a good temperature humidity measurement. And then the other one is when we kick it off. Here we're in a timer callback. This timer occurs every 1 second, and that's how often we take the temperature humidity measurements. And under normal cases, we'll see this log that says we're starting one. There happens to be an error log right next to it. This is where we can't start a new measurement because the module is not in the right state. Something has went wrong. We shouldn't be seeing that in the demo. So here we are at the console. I'm first going to reset the board by pressing the black button, and there it goes. And now you see that temperature sampling information coming out, and I'll just do a Control-L to stop that. So first thing I want to show you is the LWL status command. There's not much there, just the status, the fact that LWL is turned on, and then the put index. If we execute this a few times, we'll see the put index changing as logging is occurring. Now I'm going to do LWL test, and if you remember, what it does is it issues 4 LWL log commands, and then it disables logging. So if we look at the put index now, we notice it is no longer changing, and also on has went from 1 to 0. So now I'm going to do a LWL dump. So there's a lot of hexadecimal information. This is the circular buffer and some header information. And we'll talk more about this output format in the lesson on the fault module. But for now, I am just going to cut this data and put it into a file. So here we are in a Windows command shell in the source tree in the fault directory. I went here because this is where the formatting tool is. So I've put that LWL dump output in this file raw1.txt. Let's just cat that. There it is. And the formatting tool is called logformat.py here. We'll be talking more about this tool in the lesson on the fault module. But very briefly, to run this tool, you have to tell it a directory where it can find the source files, the .c source files, because it needs to find all of the LWL statements and get formatting information. I also need to tell it the directory containing the LWL dump output, obviously. This tool does have help, but I'll just walk you through it. So the directory where the source code is, if I point to the parent directory and this where I am, it will be able to find all of the source from that point on down. And then the file where the raw dump is raw1.txt. So we execute that and we get a lot of trace out. If you look at this, it's not too interesting. It's very predictable, or it's a pattern, a 1 second sort of pattern. We see the uptime in seconds going here. It's 31, 32, 33. We see these 100 millisecond ticks coming out. We see a start temperature humidity measurement and an end. Those measurements are being made on 1 second at a 1 second rate, so they sort of line up with the uptime. And then if we go to the end, we see these 4 test logs. And that is the result of the LWL test command. And if you'll remember, after it issued these 4 logs, it disabled LWL, and so that's why these are the last log statements printed. Here are the prompts or questions for this lesson. I'll just pause here for a moment and then go through them one by one, giving my take. How could this lightweight logging implementation be improved if you allowed the build system to create modified versions of the source code? So this is the idea where there'd be some script or something that ran before the build that would take the .c files that contained LWL statements, and it would replace those LWL statements with some kind of generated code. And then that's the code that would be compiled. Well, there's a couple usability things. I don't think the user would have to understand these logging IDs at all. For instance, those hash defines at the top of the file. I think the system that generated the code would handle that. The user wouldn't have to supply that number of argument bytes parameter, which I dislike. Again, when the scripts generated the code, it would know that. And then finally, this is sort of an efficiency thing. The creation of the lightweight logging record in the circular buffer could probably be optimized quite a bit to be faster. And I'm not exactly sure how that would work. It might be that you load the argument data in a local buffer, or maybe you could somehow load it directly into the circular buffer inline in the generated code. And sort of related to that, you could optimize special cases. For example, if there's an LWL statement with no arguments, that could maybe be handled very efficiently. How might you implement a real-time LWL viewer? In other words, to see the logging in real time as it's generated. Well, I actually did something like this once, and it wasn't too difficult. So what I did is, rather than write the data to a circular buffer, or in addition to writing data to a circular buffer, the raw LWL data gets written to a TTY or UART driver. And so the UART serial interface would be connected to a laptop, and I would have a program on the laptop that connects to the serial port, receives the LWL data, and decodes it and prints it to the screen. So, I mean, this is not trivial, but it's not too hard to do. And of course, the nice thing about this, because the trace is very compact, there's not a lot of data going across that UART serial link. What is a possible solution to avoid filling up the circular buffer with the same trace message? And the scenario here is one where you have put an LWL command in, let's say, the super loop. That's probably not a good idea, but let's say you did that, and you find that when you look at the log buffer, it's just full of those super loop logs, and it's not very useful. Now, so what might you do to deal with that? Well, I've seen this in other systems. I think Linux, some of the Linux logging systems do this. You would keep the LWL ID of the last log record somewhere in the log buffer header. So then whenever an LWL record is made, if the LWL ID matches, the last record recorded, you would just discard it. And so now if you have 100 messages in a row with the same LWL ID, you only record one of them. Now, as an option, it sort of would be useful to know that a bunch of those have been discarded. So I call it an option, but I think you would almost have to do this. The discarded log records would be counted, and then when the next log record is made for some other LWL ID, you would first insert a special record that says that a certain number of records have been discarded with, that match the previous record. And again, I've seen this in log files where it said the previous log message occurred, 1,000 times. So this might be something to consider. What are advantages and disadvantages of including a timestamp with every log record? Some logging systems have this, where every record has the timestamp. Well, the advantages are you have the time for every log record, which might help understand what is going on. The disadvantage is there might be a log records where a timestamp isn't that useful, so it would be wasted space. So I left it out in this system, my personal preference, but you could certainly include a timestamp. Maybe you just include 2 bytes. Use 2 bytes of a millisecond timestamp, and that might be sufficient to give you the intervals between logs. Now I sort of did a compromise, and that is to occasionally have a timestamp log record. So if you remember, I have every time there's a new second of uptime, I print a record for that, and then every 100 milliseconds, I print a record, and that gives you some sense of time. So this is the end of this lesson. I hope it was useful for you, and thanks for watching.